Okay, so yeah, everything I'll present today is kind of what I've been working on for the past 2 weeks. So it's still pretty fresh, and there are not like complete final evaluation runs or long evaluation runs done yet. It's more like conceptually what's new, what's happening in the code, and a few preliminary first results. But it's still a lot of content. So yeah, a lot of new things have been added. So I hope it's not going to be too overwhelming. I try to make some visualizations and stuff to explain everything, but yeah, let me know if you have any questions. There are kind of two topics that I have today. One is an evidence-based learning module that I implemented. It's similar to the previous learning module we've been using, only now only this one doesn't have a list of possible objects and poses that gets narrowed down over time. Instead, it has a list of hypotheses, so objects and poses, and each of the hypotheses gets its evidence updated at every step. So you can have more or less evidence for a hypothesis instead of just eliminating it completely. And then the second topic for today is voting, for which I already shared the report from Weights and Biases, but I made a few more visualizations to try and explain it a little bit better, and just, yeah, if anyone has some more questions there. And yeah. Okay.
Just a quick note on the Weights and Biases thing. I think there's a way to make the report publicly available, or have a public URL, because some of us don't have actual accounts. And
yeah. I wasn't sure how to do that.
Yeah.
I recorded it as PDF and then sent it in Slack, but
yeah, the PDF version is not as good, unfortunately, as the.
Yeah, it kind of inserted some blank pages and stuff.
Yeah, but I think Louis can tell you there's a particular way you can get a URL that's only, you can only send to specific people, but it'll be, you don't need an account.
Okay, yeah, then I'll ask him about that. And yeah, do that next time. Okay, yeah, then I'll get started on the evidence-based learning module. So first, a bit generally on how I define an object at the moment and how it is represented in the learning module. That kind of applies to also the other learning modules that are based on graphs. So basically, each point in the graph is defined by a 3D location and 3 pose vectors. And the 3 pose vectors kind of define the rotation at that point. And those 3 pose vectors are 3 orthonormal vectors. So they're all orthogonal to each other and they have unit length. The first one is the point normal, which is orthogonal to the tangential plane of where the sensor is. And then the other 2 are the 2 principal curvature directions, which is the maximum and minimum curvature at that point. And yeah, those 3 vectors kind of define the pose of that point or that feature. Just a few more things. Principal curvature 1 always.
Can I ask a question about that? I'm confused already. Sorry.
Yeah.
Let's go back to the previous slide. So the point normal vector is always normal,
Yeah.
right? So how does it add anything? I mean, it's always going to be like, I'm confused. Is that relative to the plane, or is that relative to a global coordinate system? Or
it's within the object models reference frame,
so,
and it kind of tells you the orientation of that point. So here is as an example, if you look at all the blue vectors here, those are the point normals, and they kind of always point away from the surface.
Got it, right? But then to represent that, it's not just a scale of value then, right? I mean,
yeah, no, the length of it is 1. So it's basically a location on a unit circle, and it can, like, the location of it is saying like which direction does the point normal point.
It says two numbers, yeah.
I'm just confused.
It's like it's three numbers because it's in 3D. It's X, Y, Z on a unit circle. So
Yeah,
it's
well,
always
maybe the question is which reference frame. And it can be something attached to the object.
I'm just missing a very basic idea here, which is, I mean, I understand the concept pretty clearly, but it seems if I have this, if this point normal is always tangential to the plane, well, I could represent the point normal in 3 dimensions. I mean, I could be pointing in any direction, right?
Yeah.
But then the other two, you say 3 posed vectors. Are the other 2 vectors also representing in three dimensions? Or are they relative to the point normal?
yeah, they are orthogonal to the point normal. So okay, so we have a unit sphere. All the points on the sphere are distance 1 from the center, and
Yeah,
it's a 3-dimensional sphere like this.
yeah.
And we have the point normal in there. It can point anywhere on the circle. So it can be an XYZ location here or here
Yeah, I
or
got
here. That's
that.
kind of just the direction of it.
Yeah.
And then that's the point normal. But if we only have that one, it only we can only say.
I understand what you're trying to represent. I just trying to understand what is actual the representation you're storing. It seems like the point normal requires what, 2 dimensions, right? And then the other 2 are relative to the point normal. Is that right? Or
Yeah,
or they 2 dimensions? How many numbers are you storing here for this pose vector?
so each pose vector is 3 numbers, X, Y, Z, and we have 3 pose vectors, so it's overall nine numbers.
Okay.
And
It's not like
the directions just kind of constrain the orientation in the tangential plane, because you could, like, if you have only the point normal, it can still be like rotated around itself in any
Yeah, I got
direction. With the curvature directions, we kind of constrain that.
Right. Yeah, there's 3 independent numbers.
Yeah.
and they're all relative to the object's orientation pose. Is that right? I'm confused there.
Yeah, well, they are all on a unit circle, and then they
All
are
right, so when you
associated
said
with
3
one
pose
location
vectors,
on the.
what was confusing me is I thought, oh, you were saying 3 one-dimensional numbers, but no, it's not. It's 9 numbers.
Yeah, no, it's just the length of them is 1, but they are on a 3-dimensional unit circle, so they have X, Y, Z coordinates.
Okay, all right.
But if it's on the unit circle, in principle, you only need 2 numbers, right? You don't need to have 3 numbers.
Yes, the third one can be derived from the first 2 just by making it orthonormal.
Yeah,
I guess that was part of what was confusing me too. So,
And can we think of this unit circle as being sort of centered, fixed on the object somewhere? So it's in the object's
Yeah.
reference frame, and so this point is, each point on the mug there will have some different point on this unit circle, but
yeah, so this one
Yeah,
would be
it's-
associated with 1 point on this
yeah.
model, basically.
I think I got it here. I just had this, when I think about 3D location, I think of 3 numbers. Right, but I think then you say, and then there's 3D location, 3 pose vectors. I was thinking, oh, well, those are unit numbers, 3 numbers too, but it's 9 numbers. So, all right, I got it.
yeah, and you need different numbers because you could have different flatnesses of the curve.
I understand
So
that.
it's just
Yeah,
the
I understand
point
that.
normal is not.
I got it. It's just.
And so just in terms of the reference frame this is in, so I appreciate like in the model, it's going to represent it in the object's reference frame, but the input from the sensory module, presumably that's in the environment's kind of global reference frame, or?
Yeah,
Or sensors are-
sensors.
From the sensor. It's like it would be the curvature direction point normal relative to the sensors.
Relative to the sensor, okay.
Right, so we'll have to convert that.
Yeah.
Okay, sorry for the distraction. I just didn't know before we got too far. I wanted to know exactly what we're storing.
Yeah, that's important.
Okay, yeah, so principal curvature 1 is always larger than principal curvature 2, and they are orthonormal to each other, so all orthogonal to each other, so they kind of span up this reference frame. And here I just kind of visualize this on a mug. So the color of it's a bit difficult to see everything, but the color of the dots shows the principal curvature magnitude, and then those vectors going out kind of show the direction that the curvature is pointing. And this is all three together. It looks a bit like a mess, but the blue vectors are the point normals. They always point away from the surface. And then the red and the yellow ones kind of span up the curvature directions orthogonal to that. And we basically store these three vectors for every point on this model. And we store also the location of all the points. And then one more detail is that if principal curvature 1 and 2 have about approximately the same magnitude, so for example, if we are on a flat surface or on a round ball, then the curvature directions are meaningless. So they could be pointing in any direction. So in these cases, we kind of disregard them and only use the point normal.
But their values are important, even if their directions are meaningless.
Well, yeah, the magnitude is used, but the directions are not used to specify the pose of these features.
Yeah.
Okay, so now I'm getting to the evidence-based model and how it works. Are there any more questions to how the morphology is kind of defined? Okay, so we have the first step, and then we have all the following steps. The first step is a bit unique in the sense that it's being used to initialize the hypothesis space. So at the first step, we sense a point in space, and then for every point that we have stored in the model, we determine what would be possible locations if we would be at this location. So for example, if I sense a point normal in space, then I can say, okay, if I would be at the top of this can, then the can would be at rotation 0. But if I would be on the side of the can, it would be rotated by 90 degrees or by negative 90 degrees. If I would be on the bottom of the can, it would be rotated by 100 degrees. And we kind of do that for all of the objects that are possible.
That's a large space then.
Yeah, so, but it's still a smaller space than if we would test all possible rotations for all the points, all the locations in the model. It's still like an informed hypothesis space.
And when you say possible rotations, is there some fixed number of rotations that you're testing?
Well, yeah, if I have the point normal and the curvature directions, then that's basically two rotations per location. It's 0 and 180 degree flip because the curvature directions could point either way. If I can't use the curvature direction because I'm, for example, on a flat surface and I can only use the point normal, then I have to sample kind of some possible poses along the remaining axis. And that's like a hyperparameter where we can say how detailed we want to test there.
Okay, so there's some, if some object was rotated at, 12.3 degrees or something in between like that, it would snap to the nearest one that we're checking there.
Yeah, in this case, if we do have the curvature direction, then we can initialize it very precisely.
Oh, okay.
Is there any sort of like simple way to specify a policy at the moment where you ignore kind of input features that don't have a full kind of 3D defined pose and just continue until you? Okay, yeah.
Yeah, that's to do that I have in the code. I mean, we'll have to deal with the case where an object only has that, like if we just have a ball, then we cannot use curvature directions anywhere. But that's kind of a special case. special case of the special case, I guess.
Yeah,
But yeah,
okay.
with all other objects, it would probably make sense to kind of first move to a place where we have curvature directions and then start initializing your hypothesis space from there.
Right. And even though it might take more steps, the kind of wall clock time might be much quicker because you're kind of focusing just on like informative points.
Yeah, and that's definitely something you see right now. If we start on a flat surface, like on the top of the can, all the following steps will take a lot longer because our hypothesis space is a
Right.
lot larger. So we couldn't constrain it with the curvature direction.
Very cool. Thanks.
Okay. Any other questions so far? Okay. So now next step, all the following steps will be testing hypotheses. So at the first step, we initialize possible locations and rotations. Now we use the incoming sensed features and displacements to test these hypotheses. Okay, so we kind of loop over all possible hypotheses. First, we calculate a test location by taking the location of the hypothesis, the rotation of the hypothesis, applied to the displacement that we just sensed. So we sense the displacement, we rotate it by how we think the object might be rotated, and add that to the location we think we were at before the displacement. So that's the kind of a search location. And then we also apply our hypothesized rotation to the sensed pose features, so to the point normal and curvature directions. Okay, so this is kind of our query. And then we go to our model and we find the nearest point stored in the model to the query location in a given radius. So for instance, this is radius 0.1, which I'm using in most experiments at the moment. So I have a query location and then I look within this radius, which points do I have stored in the model? And then for these nearest points, I calculate the error and from that an evidence for the hypothesis. So if I have any points in this radius, it can happen that I don't have any points if the hypothesis is just absolutely off. I calculate the angle between the pose features stored at these points and the sensed pose features. So what's the angle between the point normals that I sensed and the point normals that are stored here in my model? That's the pose error. And I add this to my hypothesis evidence. And then that's kind of the evidence for the object morphology.
That error is not just the point normal vector, it's all three vectors, right?
Yeah, it's all three vectors except if the curvature directions are not specified.
Yeah, okay.
And then optionally, this is the case now where features and morphology are kind of separated a bit more. We can add additional evidence for features that match. So I can also look at all the points in this radius and check if they match with the features that I'm sensing, like color, for example, or the magnitude of the curvature. And both of these things are weighted by distance from the query location. So if a point further away matches, it weights less than if.
I'm sorry, you said the curvature? I thought the curvature was part of the point normal three vectors there.
Curvature direction, but curvature magnitude is just the feature itself. Like how curved it is.
So those three vectors earlier didn't include the curvature magnitude. It was just I see. I didn't understand that.
Just the direction.
Just the direction. So if I had a saddle, all saddles would be equivalent. It doesn't matter how severe they are.
Yeah.
And you're calling that severity of the saddle more of a feature.
Yeah, because it's independent of the rotation kind of. That's
yeah. Can you on the first part of your hypothesis line there, the way you were describing it made it sound like you're rotating the object as opposed to moving the sensor. Is that?
I'm rotating the displacement that is being sensed.
So it could be the finger moving or it could be the object moving relative to the finger. You don't really, it's not the same thing either way.
Yeah,
How are you thinking about it?
At the moment, it's the sensor moving, so
Okay, all right, all
all the
right.
sensor moved, and that displacement is what I'm rotating.
Okay, it just said, the language you said earlier confused me a little bit. Okay, got it.
And what is the evidence? Is that a scalar value? It's,
Yeah, it's a float. So
Yeah,
usually it's, so basically the pose error can be up to pi,
in degrees.
pi halves. And then in radians. And then we have a tolerance value, which is the naming convention is because I'm keeping all the parameters that I can from the previous learning module, but this kind of tells us when the evidence is positive or negative. So for instance, we can say if the pose error is below 30 degrees, we add evidence. Otherwise, we subtract evidence because the pose error is just too much off. Then the evidence that is being added here is negative.
I guess there's a whole bunch of hyperparameters in how you accumulate this
So, Would a
evidence.
better term be bias instead of tolerance, since you're kind of biasing the evidence a little bit?
Yeah. So actually, let me get to the next slide. So here's everything that goes into the evidence updates. Sorry?
That's good. A quick question about the previous slide.
I have a question too.
Yeah, I'm sorry to hold you up. Just could you explain just one more time what get featured match on the very last line, the optional one? What's that doing?
Yeah, so this one, okay. How I'm imagining it is it will calculate kind of like a distance weighted error between the sense features and the features stored at those points in the radius. At the moment, it's just a binary thing. So it checks for every point in the radius, do the features match or not, using the same tolerance values as we were using with the previous learning module. And then weighing it by the distance.
So the interpretation, check me on this, is that if there are a lot of points in this radius that have similar features to what we're sensing, then we think it's more likely that it's this object.
Yeah, so
Okay.
at the moment, this is, if all the points in this radius have matching features, so all of these points have the color that I'm sensing right now, or all the points have the curvature that I'm sensing right now, then this will be 1. If some of the points on the outskirts of the radius don't match, it will subtract a little bit from 1. If the points at the center of the radius don't match, it will be a pretty low number,
Gotcha.
like close to
Yeah.
0.
Yeah, so
It's pretty interesting because like
Yeah.
there might also be, just as a side note, we don't have to get into it, but you know, like different objects are basically going to have different speeds with which they change. So like some you could imagine adversarial objects that have like different colors at every single point nearby, or like they're extremely wiggly. So like this kind of evidence update here might be object dependent, but that's a nuance that I'm sure we can worry about later.
Yeah, that's definitely a complication we should keep in mind. Yeah.
regarding the pose error and the feature match, how do you since there are different scales, right? How do you balance the two?
Yeah, at the moment, that's also a hyperparameter, and I'm not sure yet what the best values are. So there's a weight parameter for the features. So how strongly do you want to weight the features into the evidence? And at the moment, it's set at 0.5 by default. So this value will be between 0 and 1, and then it will be multiplied by 0.5. And then the pose error can be between, I don't want to say anything wrong, I think plus pi halves and minus pi halves. But I've been playing around with a lot of different parameters there, so
Okay.
I'd have to go back. But yeah, those are like all things I'm still testing and playing around with.
Okay, yeah, Jeff has a question.
Was it? Yeah, I just want to make sure. The one time we were talking, Vivian, about explicitly storing displacements. And it sounds like in this model right now, you're not doing that. You're just calculating on the fly. Is that correct?
That's correct, yeah.
Okay. And then I'm a little surprised. I don't quite understand why the curvature is considered a feature. It seems to me what we're trying to do is separate out the model into two things. It's morphology and the features that might be associated, like a specific sensory modality feature, like color.
Yeah.
And it seems to me like the curvature is part of the morphology. Am I wrong about that? How do I?
Yeah, that's true. So that's kind of a case where the categorization is looking at two different factors. So how we've been talking about it is morphology is like everything, yeah, related to morphology, which would include the magnitude of the curvature. Here I was defining morphology, like I actually call it the pose features, as features that depend on the orientation of the object. So if the object rotates, these features will be different at the same location.
Okay,
So,
is that an important distinction for you, or is that just something you did right now? I mean, it seems ultimately it doesn't seem quite right to me.
Yeah, in the code sense, it's important because I have to apply the rotation from the hypothesis to these features. So I have to rotate the point normal and curvature directions, which I don't have to do with the curvature magnitude or color or something. But yeah, I definitely agree. We should still make a distinction between like the curvature magnitude and things like color or texture. So
If you have enough just point normals, just the one vector, well, that defines the morphology too, right? If you have enough of them, I don't need the curvature component. Is that right?
Yeah,
okay,
so this works completely without the last line. It still recognizes objects.
Right. Okay, I get it.
I mean, is it fair to just have kind of structural features and non-structural features, and so it's still kind of features at points in space, but yeah, it's still I don't know. That's at least how I've been kind of thinking.
Yeah. Well, one way I've been thinking about this is that across modalities, like between touch and vision or so on, and even within vision, there are different sort of, some modules get color, some don't. The morphology component is common. I can learn the morphology object through touch and recognize it through vision and vice versa, but the actual sense features may not be able to do that. I can't feel the color, or I can't see the texture or the temperature. So the morphology is this thing that we can vote on across modalities. And so I'm trying to, in my mind, I'm trying to make a clean separation between things that define morphology and things that are on top of it, additional components. And so I think I understand here. You could recognize the object just using the point normals. You've decided to put the curvature as a feature. It's not even necessary, perhaps, to do that, right? You said you could recognize the object without it.
Right.
So maybe in my mind, I might want to come back in the future and rethink this through a little bit, but I think I got my questions answered.
Yeah, so basically the reason I made this separation there is because everything I have in the features here are things that I do not have to rotate depending on what I think the object's rotation is. And I agree, it's not really very nuanced yet. And yeah, it would be nice to add some more options where we can weigh different features more or less. So we can say we mostly want to look at the curvature and not really at the color, or not at all. And there's an option to not look at color at all. For example, one learning module may know about color, another may only know about curvature. And they can still vote and communicate.
Right. Yeah, okay, I'm good.
That works, but
Yeah, I'm good.
And what are the set of hypotheses in the beginning? Is it that's that outer?
It's locations and poses at that location, or rotations at those locations.
Okay, so but in the beginning, it's like every possible hypothesis.
Yeah, it's basically all the locations stored in the model, and then for each location, a set of possible rotations.
Okay, so that's a pretty large outer loop in the beginning then.
Yeah.
Yeah, okay.
And there's even an extra loop over possible objects too. Is that right?
Yeah.
Yeah, exactly. And then, yeah, I'll get into the more details in a bit, but since we have an evidence-based model here, we don't need to test every hypothesis at every step. There's a hyperparameter to say, okay, I only want to test the most likely hypotheses or only hypotheses above that have evidence above a certain threshold. So you don't have.
It seems like the evidence should narrow down the hypotheses. Even after the first touch, right?
Yeah, so but after, as opposed to the old learning module, you can still come back to a hypothesis that you previously had. So even though I may have like a bunch of very likely hypotheses, if I then get a lot of negative evidence for these, I can still come back to a less likely hypothesis that I previously had. If that makes sense.
Would it help to put have the different features have different types of features with different weights? Like you said, like the ones where the curvature is the same in both directions, that would necessarily be a very low weight. But if you had a very sharp edge where you have a very high curvature in one direction and low in the other direction, that would actually be more of a unique feature that you could assign a higher weight to. And you could basically, weight those points more heavily than the ones that have less or more ambiguous features.
Yeah. So yeah, this is one of those nuts and bolts that I'm still trying to figure out, and there are like so many moving pieces right now, and so many parameters I'm trying to figure out how to best set them. But yeah, that's definitely one of them. Okay, so I'll go on so I can cover everything. So
at some
just
point,
to
it
wrap
might
up.
be interesting to brainstorm. Sorry, it's just I don't know if you're already doing this, but it would be interesting to look at kind of the Huff transform approach of how hypotheses are dealt with. It sort of flips the loop a little bit. You'd never have the 4 agent hypotheses. Instead, the evidence kind of tells you which hypotheses are likely, and at any point in time, you have a distribution over hypotheses. So maybe
I didn't understand that, but it sounds similar to what we were thinking about using displacements for.
it's basically what the columns paper did too. Is that you never would.
I have to
anyway.
go back and review.
Yeah, and that's what
But-
capsules does as well.
I was just thinking here, one of the ways you can improve this is that we're working on that idea that there are also, in addition, that you can save certain displacements that you've observed over and over again, and those would be logical things to test right away. You wouldn't move randomly. You would so there would be two sort of models. There's a model of reference frames and the graph and where the features are. There's also stored displacements of components of this model. It's not, you can't store all the displacements because it's a very large number, but you do store some, and those are things you've seen observed over and over again, consistent in the model, and those would be the things to test right away. That'd be the quick test. Like if I see your eye, I don't just randomly look around and see what else I see. I'd say, oh, well, I have 3 hypotheses, nose, eyes, and mouth. 3 different directions I might go, and then trust those, that kind of thing. These are things we could discuss. I think that's the way to really narrow. Otherwise, this is a very big problem, and we need ways of narrowing it down. That's one way. Another way, I think, is just brainstorming right now. I know you want to go on, but I think we might be learning this morphology at different levels in the hierarchy, and so it's a very coarse morphology could be coexisting with finer ones, and so coarse morphology is another way of very quickly narrowing down your hypothesis.
Yeah, definitely.
All right, so we have to come back to that.
All of those ideas trying to keep in the back of my mind or on my next up to-do list. Okay, so here just to wrap up, things that influence the evidence value. The morphology error, so the angle between the curvature directions and point normals, can add and subtract evidence. Pose-independent features can add evidence, and that's weighted by just a factor. So we don't necessarily need to add those in, but they could add evidence for faster recognition. And then there's also an evidence decay factor, which I'm playing around with, that kind of just subtracts evidence at every time step. So it doesn't keep growing and growing and growing forever, but it's kind of just the most recent evidence from the most recent observations. And the evidence decay at the moment looks kind of like this function. So if the evidence value is negative, it's being pushed to, so it's always being pushed towards 0 again. If that makes sense. So if one hypothesis has negative evidence, the evidence decay will make it a bit less negative until it's at 0. Then nothing happens to it. If it's positive, it goes down.
So
Yeah,
decay,
so-
is it subtracted or multiplied?
It's added in. It's just plus evidence decay.
Okay.
So yeah, this whole thing, I'm calling it an evidence learning module because it's not really a formal probabilistic framework or anything. It's more like a hysteresis of past evidence that is being accumulated for different hypotheses. The evidence values by no means add up to 1 or anything like that. But still, it gives you a good idea of what is the most likely hypothesis at every step. And yeah, has a lot of other nice properties. What's not yet implemented is voting with evidence, which I'm imagining to add and subtract evidence. And then also what you just mentioned, Jeff, if we recognize common displacements that we stored in the model, like moving from I to I or I to no, so stuff like that. This could also add evidence for certain locations in the model. Okay. Make sense?
Yeah.
Okay, then yeah, I'll go through one example just to visualize it a bit. So this is the first step. We're sensing these pose features, so 3 vectors. This is just kind of the zoomed out view. The learning module doesn't get this view. This is just for us to see. And then this is the sensor patch that the learning module sees. At the first step, we just kind of initialize the hypotheses. So the first possible poses. We haven't moved yet. Now we moved. The red dot shows where we started, and then the black line is the displacement that we sensed. And then the other 3 vectors are the new pose features that were sensed.
How far is this on the actual picture of the cup?
So we kind of moved from, can you see my laser pointer?
Yeah,
Okay, so we started pretty much in the center here, kind of, and we moved like a little bit over here.
okay, about that much.
Oh no, actually
Okay.
we moved down. So yeah, this is the
Okay.
movement that we
All right, okay, that gives me
a
sense.
little bit.
Okay,
Okay, so and then we use this displacement and the new pose features. In this example, I'm not using any other features, no color or stuff like that, to update our evidence values for the hypotheses. And this is a little bit small to see now, but you can see some of the points moved actually off the object. That's the case when the hypothesis was, if I would have started at the corner of the scan and I sense this displacement, now I would be out here. Out here, I don't have any nearby points stored in my model, so I decrease the evidence value. So now this starting hypothesis has a negative evidence actually. So
how do you know
blue
that,
is negative, red is positive.
how do you know that the cup can hasn't been rotated or in a different orientation? Are you not dealing with that now?
I'm rotating the displacements. That's why the points can move off of the model of the object that I have.
Yeah.
So the
But-
hypothesis.
You could have been here, right? Since you don't know the orientation, but in that case, you moved in that direction, right?
I'm just saying, I sense something, I don't know where I am. I can say, oh, there's impossible points on this object, but I don't know the object, I don't know its scale, and I don't know its orientation. So I move and I'm off the object. Well, I can't eliminate that object because it could have been in a different orientation or a different scale.
Yeah, you don't eliminate.
Yeah, so each point there, I think those are showing all the possible hypotheses that are still.
Yeah.
So
Yeah.
all the, you're claiming all the hypotheses includes all the orientations of the king.
Mhm.
Oh, I see. So,
Yeah.
so there's a lot of cams that I'm not looking at.
Yeah.
Yeah, that's why, that was my high level point, is that for ancient hypothesis,
It's
it's
a
a
big
really
spectrum.
large loop.
Very, very large
Yeah,
picture.
large.
Yes. I agree.
Yeah, so I'm not rotating the whole can. I'm just for each hypothesis that I could start out at. So it's a bit small here. Each of the gray points, each of the points on the can. For each hypothesis, I have also a possible rotation. So I say, if I would be on the top of the can or on the bottom of the can, the rotation would be 180 degrees along the x-axis, for example. So if I test this bottom can hypothesis, I take the displacement, I rotate it by 180 degrees and move from that point in model reference frame. And then I look in my model reference frame, do I sense the correct features at this new location? And that might be completely off, which is where the blue points are.
All those different blue dots also represent the different orientations of the can.
Yeah, exactly.
Okay, so it's just, okay, I got it.
So can you give us a sense of, like, if you do one touch, right, like you did, how many hypotheses are there for the can?
So for example, I think in this example, it was around 3,000 points stored in the model and then around 6,000 to 7,000 hypotheses being tested. Except if we start on a flat surface, then we're testing more than that.
Okay, that's good. Big number, but we have ways of reducing that. Okay.
Yeah, and then again, you can set that you only want to test the most likely hypotheses. Here, I'm just updating all of them for visualization.
Yeah.
So yeah, we move again. In this case, we actually moved back to the starting location. So all the hypotheses are actually back to where the model locations would be. Nothing is off the object anymore. And we couldn't really add any evidence. We didn't really learn anything from that. Now we move to the left. Again, we updated hypotheses. I'm just gonna move a bit quicker through this. So while we're moving at the bottom of the mug, we can't really resolve a lot of information. It matches with a lot of all of the models just on that bottom of the cup.
Mm-hmm.
But now something interesting happens. Now we move from here to here, and the cup model that is in the YCV data set has some weird shape on the inside. It kind of like goes up and then it goes up again. I don't know. I've never seen a cup like that, but that's how it is.
But they actually took real objects and scanned them.
Yeah, I've seen that kind of thing.
Yeah, so yeah, anyway, so we're actually going up to the first fold on the inside of the cup. So now you see here this black displacement went out of that bottom plane and went up. And now you see a lot of hypotheses are receiving negative evidence and a lot of them are going off of the object. So it's saying pretty much for all of the objects, like this sequence of displacements doesn't match any of these possible locations and rotations. Only on the mug, we still see some red dots, small, hanging around here that still match up.
By the
We
way,
keep
I should point out these illustrations are amazing.
Oh, thank you.
I don't know how you do this.
Yeah, in the Jupyter notebooks, you can also like rotate the.
All right,
cup,
maybe
zoom in and
it's some
everything.
simple tool to make it work, but the hell, I've never seen, I don't know anything about it, so anyway, it's very helpful.
Yeah, I'm kind of using it to debug everything.
It is very helpful.
Cool. So yeah, so basically every little dot that you see here says, if I would have started with my initial hypothesis, then I would be here now, given the sense displacements. And then it says, okay, if I'm here now, does this match with my model of the object? All the blue dots say, no, this does not match with my model of the object. That's why they have negative evidence. Here in the cup, in some cases it matches. Actually, some cases on the top of the rim, that is if we would have started here on the first fold and then moved up. And then some other cases are here on this inner fold of the cup. We would have started in the middle and then moved up. Okay, so
if you move and then that you predict that movement would be outside of the object, then that would be considered positive evidence.
Positive evidence?
If it's outside of the object?
If you would have predicted you're outside the
Oh, if
object.
you predict it outside the object.
Do
You
you
mean if I
incorporate that?
move
or-
off of the object?
Yeah, yeah.
Yeah, so at the moment, we're not processing observations that are not on the object. So it's like the policy just moves back on the object and then we continue on.
Yeah,
But,
that makes sense.
Yeah, in the long run, we could actually make use of this information saying, okay, yeah, I should be off the object now.
Yeah,
And that's
exactly.
But that seems to make your life so much harder because you could be collecting evidence all day long, not being on the object.
Yeah.
It's like-
Yeah, no, that's true.
Yeah, so especially with
I'm not
voting, I
seeing
think.
super tie up in the ceiling, so that's good evidence. It's super tie.
Yes.
Wait till I have my Spider-Man. But sometimes it might actually be a quick way to narrow down between two possibilities.
Well, it seems like it's a quick way of negative evidence, right? You're saying, I think what you're using here for negative evidence, is a very quick way of
Yeah.
eliminating anything, but I don't know.
Yeah,
Yeah, you don't want to make the space too big.
Right, then your search space becomes huge.
So how are you determining what your next movement's going to be? Is it just random at this point, or are you?
yeah, at this point, it's random. Only if we move off the object, we move back on it, but the rest is random.
So for example, if you're looking down at the cup, it's like, okay, these are the remaining points that are actually still consistent with my previous movements. Each one of those has a set of neighboring points that they could move to at this point, and you could command that movement and further narrow down which one of those would satisfy that remaining.
Yeah, that's one of the main advantages of this new learning module. We can easily use it to write some much more efficient action policies that actually move to test hypotheses.
Well, I think, if you think about touch and I think to some extent vision too, we don't do random movements. We will typically follow an edge or a surface,
Yeah,
and just naturally do that. And so you would stay on the surface of the object and all your displacements would be valid displacements on the object in some sense. But that's a simple action policy. It's just build a system that just traces the edge. You know what I'm saying?
yeah. Yeah, and yeah, this is a really basic system and the action policy is definitely not very good. Also, we can't like move around the object, so a lot of views are very ambiguous, and we can't really resolve symmetries and things like that very easily in this example. But yeah, that's in my next steps definitely to have some more efficient action policies here. Yeah, let me go through this. Finish going through this example. So we basically, keep moving around. You see there are still some hypotheses possible for the mark for the pose. It's already saying, okay, most likely hypothesis is marked with rotation 0, 0. We have this evidence value for it. Nice thing is that in this learning module, at every step, we have a most likely hypothesis. In the beginning, it may not be very accurate, but still we have some hypothesis at every step. You see the ones that are still possible are also kind of symmetrical, which is, something else that's being tested for. We're testing for symmetry, but it's not super robust, which is, one of the main problems right now. So now in this case, we actually detected symmetry. We detected that these poses are symmetric and reach the terminal condition and classify this as a mark.
What do you? I don't understand this. Your comment that they're symmetric. What does that mean?
It means, basically that from this view, like all of the rotations of the mark, like in, I don't know. if
Oh,
you
I
see
see.
my-
I see.
If you
Yeah,
rotate the mark like this, it's always the same.
right,
kind of.
right. Got it.
The only way to resolve that ambiguity at that point is to go look for the handle.
Exactly. And
Yeah.
for a lot of the objects in the YCB data set, there's actually no way to resolve it. Like the bowl, it's just inherently symmetrical around one axis, and a lot of objects have at least one axis of symmetry. Okay, so this is really nice. And overall, from initial tests so far, this learning module seems a lot more robust. one problem is that it reaches timeout very often now, especially when we have symmetry or ambiguous views. So for example, if we look at the mark from this side view, it reaches the timeout because it says, okay, it could be the mark, or it could be the can, or it could be the side here. So yeah, this is just one run with different objects. Sorry for not having nicer results yet, but here for almost 1,000 steps in those 2 episodes, it said, okay, mark and master chef can are both consistent with my inputs.
But wouldn't that have been solved if you move further?
Yeah, you can't, in this setup, the action policy only tilts the camera up and down. We can't move around the object.
But even if so you can't determine the difference between those objects at all? I mean.
Yeah, I guess if you move to the top of the mark here.
Yeah, right. Why wouldn't you do that?
Yeah, I guess it didn't do it in the random policy.
Okay, so again, this has to do again with your random policy. You're just like.
Yeah.
It's like,
have you had a chance to connect it? Oh, sorry.
It's like you're in a field and it's all grass and you walk around in circles and you don't go to the edge of the field and see that there's a road and a tree or something like that. Okay. Sorry.
Have you had a chance to connect it to the finger? Because doesn't that kind of actually go around?
Yeah, I did. It definitely performs better than the old learning module with the finger. I didn't get to run more than one experiment yet, so I don't have conclusive results yet, but yeah. One problem with the finger is I didn't get very good object coverage during learning. So some parts were not really explored. I think that's where some errors came from there, but yeah.
I see, yeah, because I guess with the different views, you're kind of densely sampling each view, so it's a bit more systematic, whereas the finger is kind of just trying everything.
Yeah.
What do you mean by matching is a lot more robust?
Recognized with the finger.
So it's more robust to sampling new points on the object. So before, it pretty much only worked very well if we sampled the same points that we sampled during training. But now, yeah, I have some results actually.
This because of before you would throw out a result if it wasn't a perfect match. Right, and now
exactly.
You're accumulating evidence with a hysteresis, and therefore you can blur over incorrect data points.
Yeah, exactly. So yeah, that's exactly the problem. Before, if we get one inconsistent observation, it's out. You can never go back to that hypothesis. Here we can get inconsistent observations and still recognize the object if it's still the most likely hypothesis.
Okay, so you don't necessarily mean robustness to noise. We haven't put in noise in this, at least so far.
No, just robustness to sampling.
Sampling, okay.
Is there kind of an outside significance on the first sensation in that sense, like that if a kind of hypothesis wasn't initialized on the first sensation, you'll kind of never consider that starting point? Does that make sense?
Yeah, that's yeah, one problem, definitely.
So like if you kind of instead had like something where you could kind of uniformly resample that or something like that, if
well, that's a good point. Why would it be that way? Why wouldn't you, as part of your evidence, say, well, especially if my search space is still very, very large, it would seem like you'd want to go back and sort of reassess your evaluation. You know what I'm saying? Like when Niels is saying, you always start over again, or at least consider that possibility.
Yeah, and I'm thinking about going back to just initializing like uniformly sampled possible rotations, and then like assigning some evidence to the ones that match with the first observation. But yeah, I guess one reason I have done it this way so far is because this way we can really get the pose like to the 0.5 degree if we wanted to, or if we have a good initialization. While if we have to like uniformly sample, that's like, even if we sample in 45-degree increments, that's already more than 200 possible poses we need to test. So it's just a really combinatorial thing that makes it a bit difficult.
Yeah. So I guess if the first kind of starting position was kind of adversarial for some reason, then yeah. But again, that's I guess like a niche situation that can be dealt with later.
Yeah.
Well, I don't think it's a niche situation because, there's lots of things in the world where it takes you a while to even start tracking it at all, the extreme example is the Dalmatian dog in the Leaky Park, But also I'm listening to a song and I have a whole bunch of notes before I even begin to, and then like well into it, I start catching something that I recognize. So it seems like there's a lot of situations where we could be confused for some period of time, and my initial observations may be useless.
Yeah, that's true.
So again,
Yeah, I guess the way. Okay.
No.
I was just gonna say, yeah, and I guess, yeah, the way I think particle filters deal with this is just to kind of, every now and then kind of uniformly sample from the hypothesis space, and you can set like how much you want to do that. And I think bias that sampling and.
Yeah, so two things I was thinking about was either like use the point normal to inform the poses, but then for the curvature directions, which are a lot more noisy, do more sampling. And then second thing, to perhaps use the incoming votes to add more possible pose hypotheses. Like if other learning modules think slightly different poses, that we can like also consider them at the next steps.
Yeah, that would be nice, especially like in occlusion or something. You might have, I don't know, some parts of the retina or whatever that I've seen something and some parts that aren't.
Yeah. Let me go on maybe, because there's a lot of stuff, unless there's another question for now.
No.
Okay, so these experiments were using just the morphology. You see, the mark obviously has a very different color than the can. So if we actually use the features more, we can recognize those as well and do not get the timeout conditions like the 2 timeout episodes that I just showed. So that's a case where features like color can help. And here better able to deal with new sampling. This is the experiment we have in the README, where we have new sampling by moving different step size than we learned at. So we're moving in different increments over the object. And here now we get 100% accuracy. Before it was about 75%. So that's nice. It's just a really small experiment. I definitely need to run a lot more experiments to verify this. And also for noise, I'm not specifically testing that, but I'm kind of assuming that it should be more robust to noise. But have to test that, obviously.
Is it you're dealing with the different orientations and the different objects? Are you dealing with scale changes here at all yet, or no?
No. Right now,
Okay.
this is all fixed scale.
Okay, that's right.
Other advantages are, at every step we have a most likely hypothesis. It's not like we have to wait until we narrow down the possible matches to one, but we know what's most likely at the moment. We have a rough idea of the likelihood of different hypotheses compared to each other. It's easier to use this to inform actions and to make informed action policies that are more efficient. It's a nice representation for voting. I can talk some more about that later. I think it could be used for generalization and categories, because it's, even if my mark is slightly differently shaped, it hopefully would still have the highest evidence compared to other objects that are not mark shaped. But obviously still have to test that. That's speculation. And it opens up possibilities for using priors, like just initializing the evidence as not everything 0, but some of the objects may have a prior evidence based on context. And also for more customized mixing of features and morphology and other evidence sources like displacements. Yeah, so those are the advantages. Next steps I'm thinking about right now is, yeah, definitely adding voting with this evidence-based learning module.
Could you give us a clue why you think this is a good representation for voting? What are you thinking there?
Yeah, I think it will be easiest after I go through how the voting is working right now, but
Are you
just
gonna do that?
generally,
Are you gonna do
Yeah.
that? Oh, I
Yeah.
thought you were wrapping up, sorry.
yeah, I'm wrapping up the first part, the part
Oh,
about the
okay, sorry,
evidence-based
sorry.
learning
We'll
module.
keep going.
Well, one thing I'd like to see is really some sort of a noise analysis, like noise in the pose estimates, noise in the movement displacements, noise, and those
Yeah.
are, it's not clear to me how well this would work.
Yeah, definitely. Yeah, I mostly ran all these experiments today, and I'm still like, yeah, definitely want to test that.
Yeah, because if we think about applying this to real world, real sensor data or real things, it's going to
Yeah.
be really important to have at least some sort of.
Right, yeah, so the plan is also to
Yeah.
add noise to the actual sensor input.
That's what I'm saying, yeah.
Yeah.
Well, sensor input and the movement. And the, you know, pose estimates,
Yeah.
curvature estimates, all that stuff.
Yeah, so
Those are
far
honors.
I'm still working on getting all the hyperparameters and everything in the code right, and yeah, but that's definitely one of the next steps to evaluate that. And then, yeah, I think also using voting and multiple learning modules should additionally help with noise as well. Yeah, and then another major point would be to have more efficient action policies. That should also help with the timeout conditions, because we can actually move to the locations that resolve the most ambiguity and like efficiently explore the object. And then, yeah, short-term code stuff is, yeah, figuring out the right thresholds, terminal conditions, symmetry conditions, and all that stuff.
Can I add to your major list? I mean, we talked about these. I just want to make sure we don't forget them. One is the you know, sort of using displacements for improving our action policy in some sense. And the other is a hierarchical representation of morphology, which we haven't really discussed, but I think is an important part of this.
Yeah.
So
Right.
just don't forget to put those as placeholders.
Yeah, that's a really good point.
Yeah, right now.
I guess for the
module is still doing a ton of stuff, you know, representing very complex objects.
For the displacement stuff, I feel like that kind of necessarily requires the intelligent action policies. Because the no displacement is going to be more likely
Yeah.
until there's kind of a reason for it from like a bottom up.
Well, you could learn it by just by which things are consistent. Well, there's various ways you can learn it. So I don't think it's a random thing. Maybe I misunderstood your comment. I don't know.
No, I see what you're saying. Yeah, I guess I just meant like for it to. I imagine for it to really have a big effect, it would be because the action policy is tending to sample in certain ways, and so then you can leverage that.
Yes, exactly. Whether that's a bottoms up, like going from saliency area to saliency area, but mostly it would be like, you know, repeated consistency then gets stored, and the things that aren't consistent get put on. It's pretty easy to do in the neurons. Okay, it's good enough to put them in there. So I think those are going to be important to solve this whole problem.
Yeah, especially also the hierarchical point. Yeah, I would really like to get into more soon.
You know, I've only thought about it a little bit. I don't know if we've talked about it, but the idea is you've got a model at one level which is very coarse, very coarse, and yet at each point in that coarse model, you could have some refinement from the region below it.
Yeah.
I feel like that would be an interesting topic for a brainstorm, because at least in my head, it's not clear like practically how you go about creating a coarse model that kind of and that ties into kind of what you're actually observing.
All right, good point. Let's put it on a list for brainstorming.
Yeah.
Schedule it.
Okay, then another one issue at the moment is that it's still a lot slower than the other learning module. I already added, like changed a lot of code to matrix multiplications and stuff and got more than 10x speed up, but it still takes about 3 seconds per step if we are testing all hypotheses. If we don't test all, it's faster. And I think also adding more intelligent action policies and voting will definitely help. But
Right.
Perhaps there are also ways we can make the code run faster. Or definitely there are ways, but
I think we should focus on the former as opposed to spending all this, I mean, you gotta speed things up, but that's not the real solution.
yeah, it's just a little slow to run experiments.
Okay, right.
It takes
Well,
like
let's
almost an
decide what
hour.
we want to do.
But are you able to use the mega node and run like 200 in parallel, 200 things in parallel?
I have to test it, but as of yesterday, hopefully that should be fully working
And
now.
that should be like a 200x speed up right there.
Oh,
Hopefully, yeah. But yeah, yeah.
100x.
Yeah, is this?
No, we have 256 cores.
Yeah, I set the limit to be 128 right now.
Oh, okay, okay.
We can change that if we need to.
The other thing that'd be interesting with that is just flipping the loop so it's more like a Huff transform type thing rather than explicitly checking all hypotheses every single time. I'm not exactly sure how to do it, but I think there might be some potential there.
Yeah, I'll have to look into that more. Yeah. Could be nice.
Yeah, what do you mean with that? Sorry, Subsai. I'm just trying to picture it.
That's probably a longer discussion, but the Huff transform approach is just you have the space of hypotheses. You don't explicitly go through each of you as you get evidence. You accumulate. You add it to the points in hypothesis space that are consistent with that evidence. And then at any point in time to make actual inference, you pick the max, the points that have the max max evidence.
That's what we did in the Collins paper. I'm confused. Is that what you did?
It's sort of similar to the Collins paper and the capsules definitely uses that intuition.
I'm just, you'll have to explain it to me.
Yeah, it's a longer discussion, I
I'm
think.
confused by
Yeah.
that. Okay.
Yeah, I'm also not an expert with Huff transforms, so I'll have to look into it somewhere. I think, yeah, one thing that's holding me back from using more matrix multiplications for these hypothesis tests is because we have to like rotate all the displacements by different poses and stuff like that. So it's a bit, and then find the nearest neighbors in the model, and those are that's a bit difficult to do. I'm not sure how it would work with a transform, but
I'm
yeah,
not sure either. Yeah, I'm not sure either. It's just a different, it flips the loops basically.
Yeah.
So, maybe it won't lead to anything, but it's another possibility.
yeah.
Okay, so now you have another present, we got more dot point here.
Yeah, last point here is just adding a real valued feature error instead of binary here just right now kind of, and balancing the different evidence sources, perhaps adding in displacements, like recognizing common displacements, and just figuring all that out. And now then I would go to the voting, but I don't know how you guys feel, if you have more questions or if that was already too much information, or
Yeah, we can look at the voting. I go voting.
okay, you vote for voting?
Yeah.
I vote for voting.
Are you ready, or were you hoping we're gonna say, nah?
No, I was hoping you got for it.
Are you ready for voting?
All right, so this is also implemented, but it's only implemented for the old learning module, not yet for the evidence-based learning module.
Oh, gosh.
But it should be the same principle. It shouldn't be, I just don't have any results on the evidence-based one. Anyways, should be same principle. So the idea is we have actually multiple sensor patches. They may be at different locations. They may be different, size, different resolution, different features that they're sensing, whatever. And each sensor patch feeds into a separate learning module, and these learning modules vote with each other. each learning module has its own model of the object. The models may be different. They may be storing different features. They may have more or less points stored in them. Yeah, each learning module has its own model of the object, and it gets its own patch of sensory input. And then the vote contains a vote on object ID and a vote on poses and locations. Make sense so far?
Yeah, ultimately it would include scale, but we're not doing that yet.
No, she has different scales, I think, of features, right?
Those are different scales of the learning patches, but not different scales. of the
Yeah.
Not the object, no, not the
Right,
Yeah,
so,
not the object, just the
so,
patch.
I mean, in some sense, what do we know when we vote, we do a flash inference? Well, we know what the object is, we know where, its scale, basically how far away it is, we also know its orientation. And those are things that we seem to vote on, so. So anyway, but we don't have to do scale yet, we're not doing scale. So you're doing orientation and ID.
Yeah, there's a placeholder for a scale, but since we're not detecting scale right now, it's also not being voted on.
Let's put it off for now. Okay,
Okay, so voting on object ID, how it is right now, definitely open for other suggestions. It's just like a first stab at it.
well, are you saying, are you gonna vote separately on object ID and separately on orientation? Or are you gonna vote on them at the same time? Is there one representation or are there multiple representations?
It's kind of, they both interact with each other, but it's slightly different mechanisms. Maybe I'll go through it and then it
Okay,
makes sense.
all right, sorry.
So yeah, for object ID, each learning module sends out a plus or minus vote for each of the object it models, each object that it knows about. Incoming votes to a learning module are added up, and if an object's minus votes outnumber its plus votes, it is removed from the possible matches.
So one issue with that is
Yeah.
it may be some learning module can completely rule out an object.
Exactly,
But-
no, that's exactly not the case because
Yeah,
it's
that's
like
what I'm saying. yeah.
majority vote. So it's not if there's one minus vote, it's being eliminated. It has to have, the minus votes have to outweigh the plus votes.
Yeah, which could be a problem, because if one learning module is really sure it just cannot be this object, it cannot eliminate.
No, but I think she's saying when, maybe there's a confusion here. I think she's
Let me
saying-
go through it real quick and
Okay.
then.
All right,
So yeah, here's an example. Each learning one thing, not all learning modules need to know about the same set of objects. So for example, learning module 4 doesn't have a model of a cup. So it
Right.
just doesn't vote on the cup. Okay, so they all have different ideas. Learning module 0 actually, so just in this example, the cup would be the target object. Learning module 0 actually got some inconsistent input from the cup. So this one actually has a negative vote for the cup. And then all these ones have a positive vote for the cup, and the learning module 4 has no vote for the cup. So those are the outgoing votes for the learning modules. I'm assuming here that there's an all-to-all connection between learning modules, but theoretically they don't have to all connect to all. It just adds up the votes that come in from whichever learning modules connect to you.
And so here, does the green and red, does that signify? I'm
It
just trying to
signifies
see.
a yes or no vote for the object. So green is a yes vote and red is a no vote. So this line is the outgoing votes, and then this line is the incoming votes. So
Oh,
for
okay, yeah, there's not a line for, okay, yeah, that makes sense, thanks.
yeah, so learning module 0 receives 3 plus votes for the cup from learning module 1 to 3, and no minus votes for cups. And it receives 1 plus vote for the apple from LM1 and 3 minus votes for the apple from the other 3, and so on. And
Yeah, I
then
guess I'm just sort of philosophically right now against this type of voting, but maybe you can convince me.
Why is that?
Because you can't, let's say one learning module happens, you're sensing the apple, but you don't know if it's the apple or the ball, they're both curved. But one learning module definitively senses the leaf at the top. It can say it's impossible for it to be the ball. It's
but
just
but
impossible.
this doesn't allow that, nothing, nobody has nobody here can dictate to everyone else, right? Because she's.
Yeah, that's what I'm saying, that's a
Yeah,
problem.
so what I've been trying to do here is kind of
In the
find out.
pilot paper, we definitely had that. It is more, but the trick is you want to be, if you're not sure, you don't want to eliminate things, but if you're really sure there's a leaf there,
What would it be to
you
Well-
can't, this would not.
well, how
would
can
be-
you be certain it's a leaf?
Well, you can be certain it's not a ball.
So, yeah, so this is something that I'm hoping the evidence-based learning module can help with, because here in this old learning module, we just have object is possible or impossible. In the evidence model, we can have the evidence for different objects, so it can be a more nuanced vote. We can say, I'm very confident it's the apple, or I'm very
Yeah,
confident
and
it's
you
not
want
the
to
apple.
introduce noise, and so if you introduce noise, then your votes can never be completely confident, right?
Yeah. So,
So
and yeah,
I'm pushing back on the idea that I could say, I'm certain it's an apple, or I'm certain it's not a ball. Maybe that's not possible.
Yeah, maybe 100% certainty is never possible, but you can be pretty sure even with noise.
Well,
And it's just, there's no way
But this
here,
might still work. You might still reach the right conclusion.
maybe this is more of like a consensus-based thing rather than,
It's not consensus, it's voting, and it's like the majority rule.
yeah,
Yeah.
that's consensus.
No, consensus, means everyone has to agree, right?
yeah, so not everyone has to agree, because yeah, here the mark was negative in the learning module 0, and it still ended up on overall saying it is the mark. But yeah, the properties in general are what I've been trying to get out is not all learning modules need to know about all
Yeah,
objects.
that's good.
And we can deal with some noise if the majority of learning modules still consider the object as possible. And yeah, overall, I was just kind of trying to strike a good balance between optimizing for robustness and speed. So yeah, we could say we get a negative vote for the cup here, so we eliminate it, and that makes it narrow down on something faster, but it also makes it less robust to noise. So that's what I've been kind of trying to balance here.
Yeah, that's a tricky balance, but it seems like it's also somehow, if that learning module 0 is pretty certain it's not the mug for whatever reason.
Well, I
Yeah,
would
but
argue,
this one, we don't have certainties. We only have yes or no, so that.
Yeah,
so I would, even learning module 0, remember, learning module 0 could sense the object multiple times too, right? So it's doing voting with itself over time, in addition to seeing everyone else's votes. So it just seems like if you want to be able to deal with noise, that nobody can ever just totally eliminate something and say, well, I have my fingers skipped, or there's something missing here. I don't know.
Yeah, but the counter argument here, let's say you have a mug without a handle and you have a mug with a handle.
Yeah.
One of your fingers is touching the handle. Here, 3 of your 5 fingers would need to get to the handle before you eliminate it.
Well, maybe, but perhaps I grab
that
something
doesn't
and
seem
maybe
right.
I'm grabbing something and there's 2 objects in my view there, or like I'm looking at something and there's a mug and something next to it. So different columns will be looking at different things. So maybe only one column sees the handle and the other columns don't. But maybe that handle is part of the mug, maybe it's not part of the mug, maybe it's part of something else. And so I can't be certain yet.
Yeah, but this will require a majority of the columns to see enough distinguishing features.
Well, I think that's right, but that's okay. It seems like it's a good idea to do it that way. The way you just phrased it sounds like a good idea. I mean, it seems like,
Well, let's just be slow.
not necessarily. It could
Yeah,
be
but
fairly
it will be
fast.
more. I mean, Subhuta, would you agree that if once we use the evidence-based model and don't have like binary votes, then that would kind of address your problem?
Potentially, yeah,
At
yeah.
that point, you could have like a strength of vote parameter or something like
Oh,
that.
oh,
Yeah, like I said, that's
Oh,
what
I
I mean.
forgot.
Yeah,
This is binary. I forgot about that.
yeah,
So, okay, but I was zooming ahead.
yeah. I mean, there are definitely cases where you do a single sensation and you know what object it is.
Right, but so that's okay. Even what if one of my fingers, what if I grab the cup and I say that's the cup, but one finger felt something weird? Well, what that would be, what would I do mentally? I would say, that's the cup, there's something weird down here. And
Yeah,
I would
that's that-
say that's not a cup.
No, I know that. So you want to, but suppose that one weird thing really told you, oh, it's my mug because I know there's that logo that's sticking out.
Well, then maybe you have to attend to that component and then,
Maybe.
and then you'd see that, right?
But we definitely want to allow like a single sensation to tell you
Well,
what the
this
object is.
would allow, both this and the evidence-based one would allow a single sensation. You could settle on the object in a single sensation.
You could, but there are a lot of cases where it won't, I think.
Why wouldn't there be? Because,
In the maturity, you don't want to, but then with the right evidence-based weights, you could say, okay,
Yeah.
one sensation could be enough.
but it seems to me this sort of most cases would settle on one sensation. I don't see why it wouldn't.
Yeah, I guess it depends on how well distributed the sensors are on the object.
Maybe you need to do the temperature.
Yeah,
That's
right.
what
Obviously, if all the sensors are looking at the bottom of the coffee cup, it's not gonna do very well.
Yeah.
But if they're dispersed around the coffee cup, it'll do pretty well.
Yeah, it should work. Like
How
in this
are
example,
you, how are you taking advantage of the relative positions of these sensors? That's the key thing here.
yeah, that's the next step. So
Okay, you don't have that yet, or do you have it?
no, that's not in here. So now that was that.
But that just makes, otherwise it's just a bag of features, right?
Yeah.
And we know that's not good enough.
Yeah, so now that's voting on object pose. Let me go through the example here. So basically in this example, let's say we have two sensors, two fingers. One is touching the mug on the top and one is touching the mug on the handle. Each learning module sends out its current possible poses and the current pose of its sensory input. So it has the possible locations and rotations of the sensor relative to the model of the object. So that would be the green dots here in learning module 0. That's corresponding to sensor module 0. And learning module 1 has, for example, two possible locations on the top of the handle or on the bottom of the handle.
And just
then-
maybe anticipating some confusion just about what was said before, because this is taking account of relative positions. So it's what you're describing now is not doing a bag of features.
Exactly, definitely. Yeah, exactly.
Just
So
to,
this,
to make sure that was clear.
yeah, thanks. Yeah. Yeah, exactly. So that's the next step, basically. We have the sensor module location and rotation relative to the body. And with rotation, I'm saying these three vectors I talked about earlier, the point normal and the curvature directions. And in the next step, I calculate the displacement between the two sensor poses, the sensor pose of the sending to the receiving learning module. So let's say learning module 1 is sending votes to learning module 0. I calculate what is the displacement, so location and rotation, between how my sensor, like this hand on the handle, is rotated to the hand on the top of the mug. In the next step,
This is both,
Right.
this is both orientation and location, is that correct?
yeah, correct.
Okay.
But why do you need to do this? Why not just do it all in the body's reference frame?
Well,
Then you don't need to do this step.
Well, I'm doing all the matching in the model's reference frame, so
okay,
Yeah.
so that's a discussion whether you want to do it this way or do it with the body reference, right? But
yeah. So yeah, let me just finish this one real quick. So I have this displacement, location and rotation displacement. I transform the votes using this displacement. So basically saying, I think I would be on this handle, but given that your sensor is displaced by this location or rotation, you should be over here on the model. So now these transformed votes, the yellow dots, are being sent to learning module 0 over here. And it might get more votes from different learning modules. And the receiving learning module checks for each of its possible poses if there are at least n incoming votes close by. Otherwise, we remove the hypothesis from the possible matches. So in this case, the incoming votes are only close by to this one green dot. So after voting, all the other ones were removed because they didn't match with what the other learning modules were thinking. And only this pose is left over. And this is how it looks in the real model. Before voting, all the green and red dots were possible as locations for the mug. And then after voting, all the red locations were removed. All the green ones are still possible. And all the gray dots are other votes that came in from the learning module, from other learning modules. This makes sense.
Yeah, that makes a lot of sense. That's great.
I do see a lot of computation going on that I don't think Neuron's able to do. And so that's just an aside. I think it's still good, but you know, as I point out, you know, going through a body reference frame might be much more efficient. But this, it seems like we're still a step away from how Neurons do this, but that's okay for now.
Right.
Yeah, it seems like potentially the body, if you have n learning modules, you have to do, you know, n squared of these transformations from one sensor to the other. Whereas if everything is in the body's reference frame internally, then
Yeah, so we could replace this one black arrow with two, one first going to the body reference frame and then to the other learning modules reference frame. So yeah, that's could
should be pretty straightforward. Yeah.
You know, one way to just think about it is more brainstorming, is a single module does this sequentially in time, and it knows the displacement of the sensor as it moves, right? It calculates its displacement as it moves. And what we ultimately want to do is when multiple learning modules working together, they work on the same mechanism, but they're doing it in parallel. Right? I mean, that's just it's a very simple blanket statement. It want to be the same mechanism doing it in parallel. So I'm looking for that common mechanism that could work in time in one module, across time, multiple modules. I'm reminded of a paper I could show you where they show when you activate a single column, that column information goes up and down in that column, and then as soon as it does that, it starts spreading to the next columns over in the lower layers, the layers 5. And I'm just thinking it might even be a sequential step. It might be like a single column gets its input, makes its hypothesis, and then a moment afterwards, it gets other input and says, okay, now here's another input, as if I had gotten it, but I didn't, someone else got it. And I'm going to add it to my hypothesis. That's an alternate way this might work. I'm just thinking out loud. I don't know if that's useful or not, but I think Cortex will do this somehow differently.
Yeah, right now, the difference between the update within the learning module and the update from the votes is that the input to the learning module is a feature at a location, and the features that can be received can be specific to like a sensory modality, for example, also, and they are specific to the features that are learned in this learning module, and this sensation leads to an update to the possible objects and poses, and then the votes. The format of the votes is consistent across all learning modules. It's always possible objects and poses. And those are just kind of, add or subtract evidence for the poses that each learning module itself represents, while the model in the learning modules can be very different. It can contain a lot more or less points. It can store different types of features. It can be very detailed or not. And it can store completely different locations on the object, for example. That makes sense.
It's sort of, it's good enough for.
Just finish up the slides here. So, in reality, we do this with these complex 3D objects. So we receive votes for each model in a learning module and perform this update. We do this for all learning modules. And learning modules here, for instance, the one on the bottom has like a lot more features stored down here, and they may be like storing different features and different resolutions and so on. And also, as you can see, the possible locations on the objects within those models will be different because the sensors are in different locations. So learning module 1 will have different locations on the map than learning module 2 because the sensors are displaced.
Yeah.
So yeah, that's why we have to apply that post transformation to send the votes. We do this for n steps to narrow down possible votes. And every step we do an update using the sensor inputs, and then we do an update using the votes. Just a quick result. Using voting cuts down on the average number of steps needed to recognize an object. So here's no vote, it's this with voting. One little detail here is that, yeah,
I'm sorry, you're voting both on pose and in that previous slide, you're voting both on pose and object ID?
Yeah, both.
And in terms of processing that, do you kind of take in the object ID vote first? Because it seems like that could save computation time if you kind of, particularly with your evidence-based model, if you like eliminate an object ID, then you don't even need to do the.
Yeah, so the votes are all sent out at the same time, and then after that they're being received. So if one learning module never eliminated an object after receiving the votes, it has still already sent out its own votes before that happened. If that's what you're
Right,
doing.
but at least after, if it receives its votes and it first checks the IDs, and let's say there's, with the evidence-based one, there's like large negative evidence or something that passes a threshold, then you can just say, okay, we're not going to iterate through all the points in this object.
Yeah.
Because it's not. Yeah.
Yeah, definitely.
I think one question here, if you had a single learning module getting 5 times as much data, how fast would it?
That would be
Yes.
one learning module taking 5 steps, basically, right?
Yeah, and that would, what am I trying to say? So it seems like in the no voting case, it's taking close to 30 sensations for each learning module to figure out what the object is on average.
Yeah.
Yeah. And so 5 learning modules should be dramatically faster.
It should be a fifth of it.
Yeah, and with noise and other things, shouldn't really be it won't be exactly a fifth.
Yeah.
It'll be a little bit more.
I
but
thought
it's
it's
not even half, but it's
the
not even
purple, the
half.
purple bar seems too high.
It's too high,
That's
yeah.
what I thought
Well,
too.
I mean, in this example, the sensors are pretty overlapping and get very similar input. So it's not like 5 fingers that are all over the object. They still,
Okay.
like, their input doesn't like give
Well,
that
I
much.
think maybe the question is a single learning module, as it goes through 30 steps, may cover a larger area of the object than these 5 modules here in a single step. Right? Obviously, if all 5 modules are looking at the same thing, you would have no benefit.
You have no benefit, yeah.
But if I look over time, they move away, so.
Yeah, so I guess maybe that's the question. Is it a kind of some artifact of how the sampling is set up currently, which is kind of what you're suggesting here, I think.
And they also stick together, those things.
They
Yeah,
all
so
stick together.
that's some artifact of how we're feeding the data into these 5 learning modules versus something inherently with. the
I would have,
coding
yeah,
itself.
if I would have done this experiment, I would have picked 5 disjoint points on the object as
Yeah.
opposed to 5 next to each other.
Yeah.
And then that purple bar would be much lower.
Yeah.
But I
yeah.
guess as Heiko says, even with like a more intelligent sampling or whatever, like a retinal patch, like what's sampled at one point is going to be resampled by the learning modules that kind of move on to that. Like you can't necessarily get away from that in some sense.
No, but you can recognize a thing in one fell swoop if the different learning modules are looking at the extent of the
Right.
object.
Right.
Yeah, so yeah, the thing here is again, very simple action policies. All patches move together. If I put them too far apart, then it's very difficult to keep them all on the object. even
Yeah.
right now, a lot of patches are often off the object, while the one that's used for the movement policy is still on it. So
Well,
it's-
all right, but that goes back to your policy again, your action policies to say, just don't go have them go off the object for starters, right?
Or use the tactile sensors, which you can more easily distribute around. Like having 5 fingers.
Yeah, right, 5 fingers or just.
yeah, the problem with the touch sensor, I wanted to do that originally, was that during learning, it's not so, I didn't get it to cover the object as evenly as I can do it with the vision sensor.
Well, even the vision sensor, you could just say, look, you've got these objects in non-cluttered backgrounds at the moment. You could just say, hey, make all my vision sensors on the object someplace.
I'm not sure if oh, sorry.
They don't have to be together. I know they're together on a retina, but from a theoretical point of view, they don't have to be together.
Yeah, just from a testing, and remind me again, is there anything wrong if something is off the object or something?
No, the step is just being skipped for that learning module.
Okay, so that would still work. It's if you had 5 of these patches that were kind of separated.
Yeah, that actually
and
happens
every
a
once
lot
in a
in
while.
these experiments. Some of them will be off the object, some will be on, and then they just don't update their model in those steps.
Yeah, so imagine you're looking at a pencil and, the pencil is going into some image across the retina, where most of the retina won't be seeing a pencil. Most image patches will not be on it.
Right. Coming back to the issue with the touch sensor, that you don't get a good coverage of the object during training. Could you use for training the vision sensor? Because essentially we do a morphology based model. So you get the model from a vision sensor, but then use touch just for the inference.
Yeah, I'm hoping I can do this with the evidence-based model. The model that I did this with, it's too sensitive to sampling. So it just,
Okay.
didn't work with sampling new points with the touch sensor.
Okay.
Yeah, one thing is that the terminal condition is something that needed to be adjusted, and it's kind of, so a bit of a question, what's the best way to do it? So some learning modules may have already recognized the object after a few steps, but then some other learning modules may not have, for example, the pose narrowed down yet. So overall, if we want every learning module to have uniquely narrowed down the object and pose for the episode to finish, it overall takes longer than if we just look at one learning module individually. And one thing we
But
can
shouldn't it
do
be the
is say,
case? But shouldn't it be the case once the majority of learning modules have learned narrowed down the object, then everyone should have narrowed down the object, right?
yeah, the object, yes, but the pose, no.
Why not?
Why not?
Well, with the pose, we don't use a majority vote. We just use whether there are enough votes in agreement in the vicinity.
Oh, okay. But in principle, since these are rigid objects, if majority of them agree on the pose, the rest should also agree on the pose.
I'm not sure if it's always if that is always the case, especially if some models store, for example, the mark with a lot fewer points, or
Well,
But still, if there's 5 of them and 3 of them say, oh, it's this pose relative to the body, it has to be the case for the other 2 too, right? In the majority, if you're doing a majority vote.
but I think.
yeah,
even
but
though-
it's not that simple. It's that it's this specific. Yeah, I guess.
I mean, conceptually, it seems like,
Yeah, I agree. I don't, so why wouldn't it be that?
I don't know exactly how to incorporate it into the algorithm, but it seems like conceptually that should be we're going with majority vote. And
I think it's even more interesting than that. Remember, at any point in time, a lot of columns, there's a lot, if you take the visual system, there's a hell of a lot of columns, and only a small subset of them will be sampling this object. But I believe that voting would occur across all the columns, even the ones that aren't getting any input. That in some sense, the entire section of V1, not all of V1, but some area of the cortical tissue would all know that they all come to agreement, even the ones that aren't getting input and can't be voting, they should know. Because when those columns do get input, they should already be biased by the previous knowledge of all the other columns. So it's like we come to an agreement, it's shared among everybody, even the people who are not voting right now. And so everyone knows, the whole system says, okay, yeah, I know if I do get input, I know what I'm expecting, what should be expected.
Yeah, that's the case here. So if a module is not on the object, it doesn't use the sensor input to update the hypotheses, but it does use the incoming votes.
Right, so I don't, again, you can explain it later, but I don't understand this super tight comment why all the columns wouldn't have the same understanding. But for some reason, so, but you, like you said, all the voting, it wouldn't be equal, so I don't understand that.
Yeah, I think a lot of it also has to do with some hyperparameters. So for example, if you look at the last frame here, all the possible poses are pretty close together, like the possible locations on this map. But the question is, when do we say this is specific enough? Do we want it to be one specific location, or do we say, as long as all the possible locations are in a radius, it's okay? And then that is influenced by what's the radius that a vote can influence and so on. So yeah, those things play into that a bit as well. Because we're not voting on discrete sets of poses, we're voting in a continuous space of locations. Because every model may store different locations, like these points, they don't overlap. And actually, one thing I forgot to point out with this picture is you can see voting is really useful, especially on the first step. Before voting, we have all these gray dots scattered around this mark. Those are the incoming votes at the first step. And then all these votes are gone at the next step. So pretty much at the first step, like the relative sensor displacement eliminates a lot of impossible locations and poses.
That step is just a voting step, right?
Yeah. So that's, yeah, a nice thing that, like, that's not just a bag of features, but
Yeah.
it takes into account the relative displacement of the sensors, and with that relative displacements, a lot of locations on the objects are not possible.
Yeah. But you are calculating on a vote by vote basis, you're calculating the displacements of those two votes. So by 5 columns, I'm at one of those columns, I'm getting 4 votes. I have to calculate the displacement of all the other 4 columns. Individually.
Yeah.
Serially,
But
one at a time. Yeah. So
yeah, so every learning module sends out its votes and its possible pose and its sensor pose, and then the receiving module takes the sensor pose to transform the votes and take them into account.
yeah, I'm just saying computationally, it's a serial operation.
Yeah,
And it doesn't seem like that's going to work in the long run, but it could work right now, so that's good.
It's really cool to see this working, this
Yeah.
stuff, voting with poses and object IDs. That's really great.
yeah, it's
Get an initial version working, yeah. I think there's a lot of, yeah, like we're saying, there's a lot of, additional things we could do, but it's really great to see something up and running.
Right, in fact, it's working so well that we get agitated. I get agitated and I want to fix all the other problems.
And yeah, if we actually say that we terminate an episode once one learning module has recognized the object and pose, and we just say this learning module like spreads that knowledge to all the others, then the number of steps gets cut down by a lot more. So like, yeah, this bar here is 5 learning modules, no voting. Then the purple one is 5 learning modules with pose and ID voting, but all the learning modules need to narrow down to one object and one location and rotation. And then the pink and the, I don't know, lighter pink are either 3 out of 5 need to come to a conclusion, or 1 out of 5 needs to come to a conclusion. And then that's actually also a lot faster than just using one learning module.
Yeah.
And yeah, that's it.
Very nice. Thanks,
Well, thank
Vivian.
you.
Right.
Wait, how can it be fast?
Faster than one learning module.
Yeah,
Because it gets more information, it gets
From
its
the
sensory
other-
input, like the learning module, like one learning module, but it also gets the voting input, which can use it to narrow down the possible objects and poses faster.
no, yeah, no, I get that. No, that's good. I'm trying to decide between one learning module on its own versus 5 learning modules without any voting. How come there's such a big difference between them? It seemed
Oh,
like,
because all 5 learning modules need to come to a conclusion on their own. And some
oh,
need
okay.
may recognize the object faster than
Okay.
others.
But wouldn't the one all in the right be confused half the time? It wouldn't know enough.
The one learning module?
Yeah. Is that one learning module, one step?
No, it's
I
like
see.
15
That's 10
steps.
steps, I see.
Yeah.
Yeah,
It's still not obvious, okay, I don't know, not gonna worry about it.
Well, if you have more learning modules, it always takes longer until everyone got to a conclusion without the
Well,
vote.
it's not, I can see that, but I'm not sure why, it's not clear why.
I mean, on average, it would be the same, but yeah, there will be some spread.
No, because this is sort of like the max. That's just
It's the max, but there'll be some spread, yeah.
I'm not worried.
You're like every purple line is like when each individual learning module recognized the object, and it may be much earlier than some other learning modules because yeah, they get different sensory input. So sometimes it gives you more clues, the sensory input that the one learning module receives, and then they are faster than others, but it still has to wait until all the other learning modules figured out the object and pose.
Yeah, yeah. So if you were to plot the max and min for the one learning module, the max amount of time it might take, that would be closer to 30.
Right.
Yeah,
Yeah.
from 5 seeds kind of thing.
Yeah, exactly. Okay.
Good,
very
good,
cool.
All right,
thanks.
thank you, very nice.
Thanks.
All right, Jason, we see you soon. I stopped the recording and we see you soon at the
Yeah.
company meeting.